Let's get started. So today's lecture is a continuation of our understanding of differential circuits. Okay, and we started off in the last class. If I just quickly recap, so we saw how a differential pair is done, and we calculated what is the input common mode voltage range, right? In order to see what is the minimum input common mode, we said this transistor has to be in saturation, and this transistor should have the sufficient VGS. And for the maximum input common mode, this basically has to be in the saturation region, right? So we derived those things, and basically more than derived, it's basically to understand the limits of this particular circuit, right? And then we saw what happens when you do large signal behavior, right? That is, if you drive it with a very large signal, then only one side of the transistor is on and the other side is off, and so the entire I tail or the ISS flows through one side, the other side goes to 0, right? And so the large signal characteristics can be kind of drawn like this. Today we will look at the small signal characteristics. Okay. Now some of this material will be maybe you are familiar with already because of what you would have studied in your undergrad, but we will quickly go through these things. If there are any doubts or questions, please do let me know. Okay. All right. So what we saw in last class is basically what is called as a single stage fully differential OTA. Okay. Okay. So fully differential. Why we say it is a fully differential is because fully differential single stage OTA. Okay. Because you have a differential output. Okay. So you have V in P and V in M. Okay, this is R, and this is some bias voltage. Okay. Now we need to figure out which terminal is positive and which terminal is negative. Can you guess? I have two output terminals. Which one can be labeled as V out P and which one can be labeled as V out M? Okay, so let's do a quick experiment. Okay, a thought experiment. Okay, so V and P can be written as V common mode plus, let's say, a small signal. Right now we are doing a small signal analysis, right? Because most of our analog circuits work on this premise, right? So you have a common mode plus, let's say, some delta V. Okay, and this can be written as some common mode minus delta V, right? So if there is a small common mode signal, there is a common mode signal and there is a small signal riding on top of it. Okay. For example, now our differential signal is basically 2 times delta V. There is a plus delta V on the P side and minus delta V on the M side. Okay. Now what will be this node? Let's call it SP. What will be this voltage? You have, this will basically, if you if you write the KVL across this whole thing, right? So if you start from here and go like this and do a KVL, you will see that VP will be just a VCM minus the VGS required for this one. Okay, this VP has no small signal component. Okay. All right, and therefore this is called as a virtual ground. VP is a virtual ground because this node P does not vary with the small signal. Okay. Basically, you can understand it as being the average of V in P and V in M. Okay, with a certain offset which comes from the VGS. All right. So now, if you see this, what will be the current which is flowing through here? ID1. or rather the delta ID1. Okay, delta ID1. When I say delta ID1, there is a, of course, when the delta V is 0, half of I tail, if you call this as I tail, right, half of I tail will flow on each branch equally, right? That was what we discussed last class. Now, when there is a small delta V on one side, what will be the delta ID on, let's say, the left hand side one? What will be the current? You can unmute and answer. You got the question, right? So, for delta V 0, I1 equal to I2 equal to I tail by 2, correct? Now, in the presence of delta V, right? So, I1 will be written as I tail by 2 plus some delta I, correct? Delta I1. And similarly for I2. Now, what is delta I1? Remember that delta V is a very small signal. It's a small signal.
GM delta.
Exactly. Delta I1 can be written as GM times delta V. Okay. So, for delta I1, it is GM times delta V, and delta I2 can be written as what? Minus GM times delta V. Okay. So, a small example could be that, VCM is, let's say VCM is 0.6 volt, okay, and delta V is, let's say, 1 millivolt, all right. So, V in P is given as 601 millivolt and V in M is 599 millivolt, okay. Now, what happens? I1 can be written as, let's say, I tail is 1 milliampere, okay. So, it becomes 500 microamp plus GM times 1 millivolt, and I2 becomes 500 microamp minus GM times 1 millivolt, okay. All right. So, now what will be V out 1? Let's call it as V out 1 and V out 2. Now, what is the what can we say for V out 1? V out 1 can be written as VDD minus ID times RD, or rather the delta V out 1 can be written as what? Minus GM times delta V times RD, correct? And delta V out 2 can be written as plus GM times delta V times RD, correct? Because, keeping all other things constant, okay. So, so if you look at the polarity of V in P as plus delta V, and delta V in M to be minus delta V, and if you say this is going to be my op amp, okay, or an OTA, right? Let's say this is plus and minus, that is, this is V in P, this is V in M. How will you draw the polarity of a differential op amp? If, let's say, this is V out 1 and this is V out 2, which will be plus?
So V out 2.
V out 2 will be plus, because V in P and V out 2 are in phase, all right. So, this will be plus and this will be minus, okay. So, in other words, this can be written as V out P and this can be written as V out M. Now, this is also evident from the fact that if you have a common source amplifier, right, there is a 180-degree inversion between the input and the output. So, directly you can say that whatever is connected to the drain of the left hand side transistor will be the V out M. Okay? Both ways to understand. All right. Now, I hope you are familiar with the concept of half circuit. What is half circuit? differential mode half circuit and common mode half circuit. Let's look at the differential mode. Basically, you can say that this circuit is quite symmetric, right? And for a differential signal, okay, we saw that this node P is insensitive to it's basically insensitive to the small signal variations, right? Because if you draw the KVL here, you have V in P minus this VGS plus delta V and this one, and then you have minus VGS minus delta V plus V in minus delta V. Basically, you will get VP being the same as VCM minus VGS, which will be your VP. Okay. So this is the virtual ground, as I mentioned, right? So now what we can do is you can kind of split this circuit, okay, into half, right? So you take this and you split it into half, okay, and basically this is virtual ground, and therefore if you split it into half, what is the half circuit that you get? You have a resistor, you have one side transistor, and then you get a virtual ground. Now what is this amplifier? This is nothing but a common source, right? Now all the different variants that we studied about common source amplifiers, right, can be used here. Okay. So you can have, and all the analysis that we did for common source, both in terms of gain, right? So what is the gain? It is nothing but minus GM times RD, right? And output impedance, R out is basically RD parallel to R naught, which is typically can be nothing but RD, and then bandwidth, and then noise, input referred noise, the linearity. All these things we have already seen, okay? And all the small signal analysis and the stuff that we did in the previous module for common source amplifiers can be basically reused here. Okay? And therefore, you can also have the other variants that we talked about. Okay, you instead of this resistor, the same thing happens if you try to increase RD in order to improve your gain. You end up with the crunched voltage swing at the output. Okay, the V out DC or the V out common mode, as we call it. V out common mode, as we saw here, V out common mode is nothing but VDD minus ID RD, or I tail by 2 into RD. Okay, so if you keep increasing RD, what will happen? V out common mode will basically keep coming down. That means there is very less amount of voltage for your output to swing before your transistor goes out of saturation region. Okay, so your swing limits get crunched heavily. Okay, so the other thing is basically to say that you have a now what is this load? Now what is this circuit basically? Common source with the what type of load?
Active current source load.
It is not an active current source, it's basically a current source load. It's a current source load. So the half circuit will basically look like this, right? What is this? Right. So the differential mode half circuit will basically look like some VB with this one. Again, all the analysis that we have seen, okay, everything comes into the picture. Okay. So you can have a current mirror load also here. Okay, you can have resistive load, current mirror load, things in triode region. You put a MOSFET in triode region. You can do all that stuff. Okay, and you can also have source with source degeneration. Basically, that is, if you have RD, you can put a MOSFET here, right, and put some resistor here, some RS here. Okay. Now the differential mode half circuit will look like RD, this with RS. Okay. Now this is a common source with a source degeneration. This RD can be replaced by a current source or a current mirror load, whatever it is. Okay. So all that we saw in the previous module under common source, the same thing applies here for differential mode circuits. Now what is the differential mode circuit? Okay. So many times you will basically have, let's say, so when somebody asks you the differential mode gain for this differential pair, all you need to do is basically, first step is to convert it to a differential mode half circuit. Now analyze the half circuit for all your gain, bandwidth and other things. Okay, all the other parameters. Okay. Now you will basically have V in 1 and V in 2. Let's say we have arbitrary signals, two signals V in 1 and V in 2. Now how will this circuit behave? Okay. So now the differential mode circuit, the differential voltage VDM, the differential mode voltage, as I mentioned, can be taken as V in 1 minus V in 2, and the common mode voltage can be taken as V in 1 plus V in 2 by 2. And therefore, V in 1 can be understood to have V in 1 minus V in 2 or by 2 plus V in 1 plus V in 2 by 2. And there same way V in 2 can be understood to have V in 1 minus V in 2 by 2 plus or rather it is the other way around, V in 2 minus V in 1 plus V in 1 plus V in 2 by 2. Okay. So for arbitrary signals, this is how you understand it to be. Okay. So the output can be written as the differential mode gain into the differential signal and the common mode gain into common mode signal. So now let us look at the common mode half circuit. Now what is common mode half circuit? I'll just take this example. So whatever be the load or whatever be the signal circuit here, basically you can use the same thing. Now this is RD, okay, M1, M2. Now when we say common mode, we basically mean that both sides are given the same input, common VCM in. Okay. Now how will you analyze this circuit, or how will you form the half circuit for a common mode input? Okay. Now when both the sides are having the same signal and there is a common mode input, this node P is no longer a virtual ground, right? It becomes a virtual ground because one side you have plus delta V, another side you have minus delta V, and therefore you can talk about a P being a virtual ground. But for a common mode input, when I say common mode input, it means that for example, VCM in can basically have a certain DC voltage, VCM DC, with some AC voltage, some noise. Okay. So this comes for both the P and the M side. In this case, so I was telling you about how this node P is no longer a virtual ground, and therefore you cannot directly take it to be here. Okay. And I was explaining that VCM in is not necessarily only DC. For example, in the last lecture, I mentioned that if this differential signal is running close to some clock line or some noisy power supply line, there will be some disturbance or common mode noise. Okay, so that is what is called as common mode noise that can ride on top of your DC voltage. Now for this node P is not going to be at virtual ground. So how can we draw the half circuit? Basically use split it in the middle. Okay, so your common mode half circuit can be written as RD, the transistor. Okay, and this node P, this current source can be split into two. Okay, So this becomes I tail by 2. Okay. Now if you use a transistor to implement this current source, right? Now this current source will basically have, I tail with some, let's say, R tail. There will be some finite output impedance for this one, which can be written as R tail, right? And now when you are splitting it into 2, how will you split it? Because if you join the 2, you should get back the original circuit, right? So I tail by 2, this can be split into I tail by 2 and 2 times R tail, right? So that this into 2, right? So when you attach 2 current sources in parallel, it becomes the sum of 2 current sources, and put these 2 resistors in parallel, you get R tail. So it has to be 2 times R tail. So our common mode half circuit can be written as RD and our transistor with R tail by 2. Okay, with of course I tail by 2. But then for a small signal analysis, you don't consider this I tail. So now for small signals, it basically is RD and this is not R tail by 2, it is 2 times R tail, right? Now, what is the gain between V in and V out? So V out Cm by V in Cm. There is common mode output to common mode input. What will be the small signal gain? So when I say small signal, don't confuse. When I say common mode small signal, don't confuse with common mode DC. Common mode DC is the DC biasing point that is coming into your differential amplifier. That's just a DC. Okay. When I say common mode AC, it is basically the common mode noise or some common mode signal which is riding on top of your existing signal. Okay. That is why I wrote these equations. When you have arbitrary inputs Vn1 and Vn2, okay, you can write the common mode voltage to be the average of the 2 signals. Okay. So that will have both DC component and it can have common mode DC and common mode AC. Okay. And therefore, we are talking about the common mode AC. What is the transfer function or what is the gain? Now, what will be the gain? This is nothing but a common source with source degeneration, correct? And therefore, what was the gain? It was Gm times Rd divided by 1 plus Gm Rs, okay, or Gm plus Gmb Rs, correct? Now, in this case, what can we write it? It is Gm times Rd divided by 1 plus Gm, 2 times Gm plus Gmb times R tail. Okay. Now, this is what you call as your common mode gain. Okay, common mode gain. And previously, in the previous slide, what we or a couple of slides before, what we derived, okay, is nothing but your differential mode gain. This is your ADM. Okay, your differential mode gain. You take the half circuit, you analyze this. Here the gain ADM is given by nothing but minus Gm times RD. Correct. All right. Now this is your common mode gain, and therefore we can define a parameter. Okay, for small signals. Okay, when Vn1 and Vn2 have both common mode and differential signals, right? So the V out, small signal V out, can be given as ADM times Vn1 minus Vn2 plus, right, ADM times Vn1 minus Vn2 divided by 2 and ACM times Vn1 plus Vn2 by 2. Okay, or in other words, all these are small signal quantities. Don't add the DC voltages. Okay, this is the caveat. Okay, in other words, ADM times small VDM plus ACM times small PCM. Okay, Now you can look at it a little intuitively also for the differential mode circuits. Let me just go back here. Okay, you correctly pointed out that delta I1 is GM delta V and this is minus GM delta V, and we wrote that delta V out 1 is minus GM delta V, delta V out 2 is plus GM delta V times RD. Now the effective delta V out can be written as V out 1 minus V out 2, or rather, sorry, V out 2 minus V out 1, because that is plus minus this thing. You will get 2 times GM delta V times RD. Okay, and therefore delta V out by delta V, it is nothing but GM RD. It is because the differential mode signal here is VDM is nothing but 2 times delta V, correct? Because you have plus delta V here, minus delta V here. VDM is nothing but V in P minus V in M, okay, which is given as 2 times delta V, right? And the gain is nothing but GM times RD. Okay. So you can kind of intuitively look at this circuit and arrive at it, or you can also go through this half circuit. Half circuit is the safest way. You can go through this and you can look at it. Okay, and basically you can say that ADM times VDM is your differential mode gain, and ACM times V will be your common mode. I mean ACM is the common mode gain, and you get the output. Okay, all right. Now your actual output will be this plus V out common mode. Your actual V out can be written as V out common mode plus ADM times DM. Of course, when you say V out, which is nothing but V out 1 minus V out P minus V out M, therefore this common mode does not come into the picture. Okay, but then you can look at the for a single, so for V out P, you can basically write it as ADM times minus VDM by 2 plus ACM times VCM by 2, and V out M can be written as ADM times plus VDM by 2 plus ACM times VCM. Okay, or sorry, VCM, because VCM is anyway given by the average of the two signals. Okay, and VDM is given by V in 1 minus V in 2, the difference of the two signals. If you define these two like this, V out this plus of course V out common mode. You understand? So you have a common mode, V out DC common mode, plus you have some small signal differential voltage and a common mode voltage. Okay. Now I am sure you all are aware of this parameter called as common mode rejection ratio. Right? Common mode rejection ratio, which is also called as CMRR. CMRR is defined as what? It is the differential mode gain divided by the common mode gain. Okay. So for that simple differential pair that we drew, okay, the differential pair's common mode gain is GMRD, right? And what is the differential mode gain is GMRD. This one is GMRD divided by 1 plus 2 times GM plus GMB times RT, right? So therefore your CMRR is nothing but 1 plus 2 times GM plus GMB times RT. Okay. This is the common mode rejection ratio of your simple differential pair. Okay. Now what do we learn from here? Basically what is common mode rejection ratio? That is, if your input voltage has got both differential terms and the common mode terms, okay, we are talking about AC terms, okay, DC we have separately looked at, right? AC terms, if they are there, right, what happens is basically that the gain of your common mode signals is much lower than the gain of your differential mode signals. And therefore, if you look at the output, you will see that there is a good amount of discrimination between the differential mode signals and the common mode signals. And the common mode signals are rejected. Okay, they are rejected by this ratio of CMRR, and which is given by 1 plus 2 times GMRT or GM plus GMB RT. So in other words, what do we see here? If you make your, so CMRR is directly proportional to your RT, correct? In other words, if the tail current source, okay, now go back to your current sources which you designed, right? If you take a MOSFET, its R tail, if you just have a simple current source, its R tail is given by R0. Okay. So the better the current source, the better your CMRR. Right? So if you have a better output impedance for your current source, it improves your CMRR directly. Okay. Now, of course, CMRR also depends on GM, and therefore you can use this. Okay. So you can, there are different ways by which you can look at all these things. Okay. And I will give you some. Please go through the textbook. We have looked at these things. All right. Now, in the presence of capacitance, what happens? Let's look at the bandwidth of this whole thing, right? So for a common mode signal, for a differential mode signal, right? In the presence of you can basically, let me, for the fun of it, to give a variant, let me put a current source load. So this is a very commonly used topology. Okay, this is what is called as a 5 transistor OTA, because this is a fully differential OTA. Next we will see a single-ended OTA, right? So this is V out P, this is V in M, this is V in P, and this is V out M. Okay. So typically what happens is you will have an output load. Okay. Now just a side note here, many times I use this word OTA or operational transconductance amplifier. So as long as you have, if you have only capacitive loads, okay, when I say capacitive loads, if you are driving only capacitors and not resistors, an OTA is sufficient. Okay. So if resistive loads are present, okay, you need to have an OTA plus a common drain or some output driver, okay, such that it can drive the resistive load, and this becomes an op-amp. Okay. So although this is the more textbookish distinction, many times the word op-amp is used commonly for OTAs as well as op-amps. Okay. And in MOSFETs, as you would see, in many cases you will have only capacitive loads, and therefore you will, because what happens is this MOSFET, this op-amp will go and drive another op-amp or another transistor's gate, okay, where the input impedance is only capacitive. Okay, so the times you will have only capacitive loads. So therefore, this is also called as an op-amp. Okay, so don't get confused by the interchangeable use of it in literature or for that matter in other things. Okay, but this is basically the distinction. Okay, so this is a fully differential op-amp. How to generate this VB, we will look at it at a later lecture. Okay, so if you have some load capacitance, now this load capacitance can be the capacitance presented by the next state, okay, by the routing capacitance and other things, and also the drain to bulk capacitance of these two transistors. Okay, so if you say this is M1, this is M2, this is M3, and this is M4, you have the drain to bulk capacitance and the gate to drain capacitance. You can use Miller's effect and then see what is the capacitance that is seen. Okay, you have some load capacitance. Now, what will be the mostly we are interested in the differential mode performance, and therefore, what is the bandwidth of this signal in the differential mode? It is nothing but 1 by 2 pi R out times CL. Okay. So since it is differential, half the signal goes in P side, half the signal goes in M side, and therefore the expression remains the same. Basically, you go from here to the differential mode half circuit, right? So there it becomes like this. This is V in, this is VB. You have CL, and therefore R out here. What is the R out here? Let's say this is M1 and M3. What is R out? Can maybe unmute and answer.
R03 parallel.
R01 parallel to R03.
Exactly. R01 parallel to R03. Correct. This is your R01. Okay. So all the analysis that we did in the previous section, previous module, they basically directly they appear here. Okay. All right. And I did mention in closing what I would do is basically I did mention this having source degeneration for the differential pair. So this is a basic differential pair. So I mentioned that all right. Now this basically can also be written as, let's say this is I tail. It can also be realized as something like this. This is RD. You have two MOSFETs, right? And you have a single resistor whose value is 2 times Rs. Okay, and what happens is you have I tail by 2 and you have I tail by 2. So you will see circuits like this. Now, how do you analyze a circuit like this? I mean, instead of resistor, you can have capacitor, you can have any kind of thing, right? How do you do this? You just draw the half circuit. Basically, it becomes like this. You have Rs, and then for this is of course the virtual ground is in the middle. This is a DC source, so this will be your differential mode half circuit. Right. And for your common mode half circuit, of course, Rs will come in parallel with your RT. All right. So this is what is called as a differential mode signal. Okay. Now, till now we have assumed, okay, that both the sides of a differential pair are exactly symmetric, okay, or they are exact replicas of each other. But we know that from our discussion earlier about mismatch and variation, we know that M1 mismatch happens, and therefore M1 is not equal to M2 and RD1 is not equal to RD2. So this happens very commonly because this is something that we expect. The IC design thing is extremely, I mean, the process is very not at all. I mean, it has a lot of randomness associated to this, right? And therefore, you will have some amount of mismatch happening here. Now, what will happen if there is a mismatch? Basically, what will happen? You can understand that there is a you can see that there is an existing mismatch which happens between the two resistors that will automatically give rise to some kind of a differential output even for common mode signals. Okay, so that is basically what is called as a common mode to differential mode conversion. Okay, so if you have mismatch for common mode signals, okay, there will be a differential mode output. So this is what is called as a common mode to differential mode conversion. And you'll also have differential mode to common mode conversion happening. So that we will see in the next class. All right. So we'll wind up the class with this. Any doubts? Any questions? So I will kind of go a little deeper into M1 and M2 not being equal, or RD1, RD2 not being equal. And we'll see in the next class how we can build a single-ended OTA, which is very, very commonly used. Okay. And then we will move to all the other op-amp. So this is a simple op-amp design, and we will go over the other op-amp designs. Okay. So now the other thing is your. So I do understand that some of the groups are having classes at 11:45 now. So those groups can. So in that case, what we will do is the MTech PhD groups. Please stay back. And if there is a group where all the members are not having class, please stay back now. The rest can, log into the same Zoom meeting at 4:10. Okay. And one more thing, we need to kind of cover a little bit of ground here, because your projects have to start by this week. So what I will do is every day in this week I will post a lecture. Okay. Tomorrow we have class in the 4th hour, and we have already lost 2 Friday classes because of the quiz. And so because of that, what I will do is Wednesday and Thursday I will record a lecture and I will post it. Okay, because it is very difficult to find a common slot for all the students, and I will record a lecture and put it. So please watch the lecture every day, and on Friday when I come, when we have the class together in the 1st hour, I expect that all of you have watched the Wednesday and Thursday's lecture. Okay, so each day I will talk about. Sorry.
Can you record the lecture and put on a Friday or something so that we can watch it over the weekend?
So what I will do is, anyway, I also have quite a bit of work. So what I will do is I'll record the lecture on Wednesday and Thursday, 1 lecture per day, and I'll upload it. So of course all the lectures are getting uploaded. So it will be good if you can watch it on Wednesday, Thursday before Friday, right? Whenever you have free time, because some students will have certain hours free and some other students will have certain other hours free. Because the worst case is that you watch over the weekend, but that's the suboptimal solution, because it will be good if you can do it on Friday. Okay. Yeah. All right. So during this week, I will cover all the op-amp designs. We will look at all the things. So today we covered the fully differential single stage differential pair, differential OTA. We will do the other stuff from tomorrow onwards. And tomorrow's class, I thought I will just show you a small demo of how to design a simple op-amp, and that should help you in designing these circuits and also doing your thing, because many times what happens is students find there is a bit of a leap between what you do as a theory and what you do when you design. So just to kind of bridge that gap, I will try to do a demo session tomorrow. So it'll be good if you can kind of have your LT spice around. It'll be good. Okay. So now we will wind up today's class, and let's have the discussion for the MTech batches first, MTech PhD groups, and also those BTech groups who do not have class right now. Okay. The others can join at 4:10. I want to finish it today. Thanks everyone. Have a nice day.